exit angle for the guide vane, full stop. Assume inlet diameter is equals to 2 times outlet diameter. Assume inlet diameter is equal to twice the outlet diameter, full stop. Hydraulic efficiency is 80%. Hydraulic efficiency is 80%. A constant radial velocity of flow is a constant radial velocity of flow is 3.6 meter per second. 3.6 meter per second through the runner. Through the runner. Come on. Mechanical efficiency is 95%. Mechanical efficiency is 95%. Come on. Width ratio is 0.1. Width ratio is 0.1. And water leaves the runner radially. Water leaves the runner radially. Water leaves the runner radially. Yes. So it is very similar to the previous problem. Means yesterday already we solved one problem. Okay, it is a very similar. Yesterday also we calculated one is an inner diameter and outer diameter. Okay, and the inlet and exit angle for the vanes. So that is beta 1 and beta 2, and exit angle for the guide vane. So guide vane is nothing but it is a stationary. So we can call it as a nozzle. So we have to find out what is alpha 1. Okay, what is alpha 1? So while coming to this data, so once again it is an inward flow reaction turbine. Inward flow reaction turbine is nothing but, okay, always D1 is greater than D2. Okay, always D1 is greater than D2. So the given power, so it is a 300 kilowatt at 200 rpm. Speed is 200 rpm. The active head at the turbine is 18 meter. So they given the net head or the active head. So it is an 18 meter. So determine the outer and inner diameter. So we have to find out D1 and D2. Also we have to find out the inlet and exit angle for the vane. See, vane is nothing but it is a rotor. Okay, it is a rotor angle. Rotor is nothing but it is a rotating part. So we can call it as a beta 1 at inlet and beta 2 at outlet. And exit angle for the guide vane. Okay, guide vane is nothing but it is a stationary. Okay, it is a stationary. We can call it as a nozzle. So that is alpha 1. Anyway, alpha 2 always it is a 90 degree. Okay, in the Francis turbine, always, okay, alpha 2 is 90 degree. Please keep your mind this point. Okay. So next they given, assume inlet diameter is 2 times the outlet diameter. So D1 is equals to 2 into D2. Hydraulic efficiency is 80%. A constant radial velocity of flow. Okay, so here radial velocity is nothing but it is a flow velocity. Okay, radial velocity is nothing but it is a flow velocity is constant, means throughout the turbine it is a constant, means Vf1 is equals to Vf2, that is 3.6 meter per second. Okay, Vf1 is equals to Vf2, it is a 3.6 meter per second through the runner. Okay, and mechanical efficiency is 95%. and the given width ratio. Okay, width ratio is nothing but okay b1 by d1 is 0.1. Okay, and water leaves the runner radially. See, water leaves the runner radially is nothing but okay, so v2 is equals to vf2. So here only I mentioned, so v2 is equals to vf2. Okay, so before going to this problem, first you have to draw the velocity triangle. So I written here. Okay, I written here. So this is the inlet and outlet velocity triangle for Francis turbine. Okay, so first first we have to find out the diameters. Okay, first we have to find out the diameters. For that diameters, okay, we don't know what is discharge. Okay, we don't know what is the discharge. But before that, okay, the given one is a mechanical efficiency, another one is a hydraulic efficiency. Okay, by using this data, we can calculate the overall efficiency. Okay, we can calculate the overall efficiency. Overall efficiency is given by okay mechanical efficiency into the hydraulic efficiency. Okay, so we will get the overall efficiency is 0.76. See, please take your calci, okay, and calculate along with me. I'm audible?
Yes, sir. Yes, sir.
Yeah. So along with me, okay, you just calculate. See, anyway, you'll get the solution here, but please practice once. Because in yesterday's problem, they given the overall efficiency. Okay, they given the overall efficiency, but today's problem, okay, we don't know overall efficiency, but to calculate overall efficiency, they given hydraulic efficiency as well as the mechanical efficiency. By using this data, so we can calculate the overall efficiency. You got 0.76.
Yes, sir. Yes, sir.
Yeah. So next, I'm going to use overall efficiency equation. So it is an a P by WQH. So by using this formula, okay, so easily we can calculate what is discharge. So easily we can calculate what is discharge. See, once you calculated, let me know.
Yes, sir, completed.
So I got Q is 2.23.
Yes,
Yeah.
sir.
So next find out diameter. So we know the equation. So Q is equals to area into velocity. So that is discharge is area into velocity. So here the area is pi d1 b1. So velocity is flow velocity into vf1. But in the last problem, in the last class problem, okay, they given the area blocked. Okay, whether it is in a 5% or 10% or 90%. But in this problem, okay, they not given the area blocked. So we have to find out diameter. Okay, so we know the discharge q and the b value, the width value. So here b1 by d1 is 0.1. b1 is 0.1 into d1, and VF1. So already given the flow velocity. So it is in a 3.6 meter per second. So please calculate and tell what is the value of diameter. So that is the outer diameter.
Sir, 1.41 meter.
1.41 meter. Yes. Forgot 1.405 meters. Correct. See, once you know D1, then easily we can calculate D2 because in the data they given D1 is equals to 2 times D2. Okay, that is twice the outer diameter. So calculate what is D2.
Yes, sir. 0.7028.
Yeah. Here only we can conclude. So outer diameter, okay, outer diameter is greater than the inner diameter. Okay, so D1 is greater than D2. Okay, see if you are getting while calculating, if you are getting the reverse, okay, then you have to change. Okay, so this is one is the alternate. Okay, while calculating. Once you know D1, so then calculate what is the width at inlet.
Sir, the ratio will remain same, no, sir.
Which one?
Sir,
D1 by
B1
D1,
by
right?
yes,
Yeah,
sir. B1,
yeah, it is point
B2.
1. D1 by D1, it is a point 1.
And what about B2, sir?
Which one? Say B2 here, they not us, no. So only we have to calculate the width at inlet. If they asked, okay, then we can find out. So Q is equals to, so pi D2 B2 into VF2. So whatever this equation, okay, so we can use it for even the outlet. So Q is equals to pi D2 B2 into VF2. Once you know outer diameter and inner diameter, then calculate the blade speed velocity U1 and U2 at inlet and outlet. You got U1 is equals to 14.72.
14.765.
Okay. U2?
7.359.
Okay. Next, draw inlet and outlet velocity triangle. Draw inlet and outlet velocity triangle. After velocity triangle, so we have to find out the viral velocity at inlet. Okay, because we have to find out alpha 1, we have to find out beta 1. So we know the hydraulic efficiency is given VU1 U1 by GH. The hydraulic efficiency is given by VU1 U1 by GH. So by using this equation, so easily we can calculate. So what is VU1? So how much you got VU1? Finished?
Sir, 9.567.
9.567. Okay. Yeah. After calculating this, okay. So if you already drawn the inlet velocity triangle, okay, you just check the value u1 and vu1. Okay, you just check the value u1 and vu1. So u1 is 14.72 meter per second and vu1 is 9.59. So in this, okay, in this vu1 is less, but see from the velocity triangle, okay, vu1 is greater. Okay, I'm right. So vu1 is greater, but after calculating, okay, so u1 is greater than vu1. Okay, so u1 is 14.72 and vu1 is 9.59 meter per second. Okay, so we have to modify it, means we have to change the direction. Okay, we have to change the direction. So we have to, initially this is in this direction. Okay, so but as per the condition, okay, we have to change the direction. So we have to modify the inlet velocity triangle. Okay, so you can check here. Since vu1 is less than u1, okay, the inlet velocity triangle is to be modified. So this is the modified velocity triangle. So I hope you understood this condition, because once you calculated u1 as well as vu1, not here, okay, even in first unit also, okay, you have to take care of the velocity triangle. If it is remains same, okay, no need to modify. Okay, but in this condition, vu1 is lesser than u1. So we have to modify the inlet velocity triangle. So please modify the inlet velocity triangle. Okay, after this modified velocity triangle, okay, so we have to calculate what is alpha 1. We have to calculate the alpha 1. See, already we know the flow velocity, okay, and we know the will velocity at inlet. Okay, so we can use tan alpha 1 is opposite by adjacent. Tan alpha 1 is opposite by adjacent. So vf1 by vu1. So calculate what is alpha 1.
So 20.62.
Okay, correct. Similarly, calculate uh, the rotor angle at inlet. So calculate first beta 1 dash. First calculate beta 1 dash. So then 180 minus this angle, it will gives beta 1. So beta 1 dash is tan beta 1 dash is given opposite by adjacent. So adjacent is this distance. So U1 by VU1. So calculate what is beta 1 dash. So tell what is the beta 1 value?
It's 145, sir. 0.29.
145. Okay. So I got 144 degree. Okay. Similarly, calculate the beta 2 from outlet velocity triangle. From this outlet velocity triangle, okay, calculate what is beta 2.
Sir, rotor angle is also vane angle, no, sir?
See here, one is a guide angle. Guide angle, it will act as a nozzle. Okay, it means it is a stationary. So it will gives only alpha. Okay, rotor angle at inlet is nothing but beta 1 because it is a rotating, no? Okay, it is a rotating, means once the water is entered and once the water is leaving. Got my point? If you want, I will show here. So in this, okay, so now the here, this is the guide blades. Okay, so we can call it as an alpha 1. Anyway, alpha 2 is 90 degree. Okay, so once the water is guiding to this blade, okay, so here the water is entering for the rotor blade. So this inlet, okay, so here the inlet we can call it as a beta 1. Okay, and the water is leaving here. Okay, entering is here and the water is leaving here. So this we can call it as a beta 2. I hope you understood, Mohammed.
Yes, sir. Yes, sir.
Okay. So what is beta 2 value? Same, tan beta 2 is opposite by adjacent. So calculate what
So
is
26.06.
okay. Okay. So you feel any difference between the previous problem and this problem? So both are same, means the procedure remains same. Okay. So what about others? What about others? Okay, just I will read this problem. Inner and outer diameter of Francis turbines are 30 centimeter and 60 centimeter respectively. See, in this problem, directly they given the diameters. But in previous two problems, okay, so they not given. Okay, we have to calculate. But in this problem, directly they given. So inner and outer diameter. So inner 30. So we can call it as an D2, and outer we can call it as an D1. So it is in a 60 centimeter. So water enters the turbine at an angle of 20 degree to the wheel tangent. It leaves the turbine radially, means the, you just read this statement. Okay, which angle is this? Which angle is this? Water enters the turbine at an angle of 20 degree.
Alpha 1, sir.
Yes, correct. It is an A, alpha 1, because to the wheel tangent. It leaves the turbine radially, means alpha 2 is 90 degree. Okay, always alpha 2 is 90 degree. If the velocity of flow remains constant throughout the turbine at 3 meter per second. So they given Vf1 is equals to Vf2 as 3 meter per second. And speed of the runner is 300 rpm. So they given N. Calculate inlet and exit blade angles. So we have to find out beta 1 and beta 2. Theoretical power developed if the width of the wheel at inlet is 15 centimeter. So what is this 15 centimeters? So width. So they given B1. Okay, theoretical power developed if the width of the wheel at inlet is 15 centimeters. So they given B1. The thickness of the blade is neglected. Okay, what does this mean? What does this mean? Thickness of the blade is neglected means, okay, in the first problem, okay, what they given, they consider, we have to consider the 5% of the area blocked. Okay, but here, okay, if area blocked is there, okay, so we're going to neglect that one. Okay, so the similar problem, okay, once again we have to find out beta 1 and beta 2, and here we have to find out what is power. Okay, we have to find out the power, but uh, remaining thing is same. Okay, the procedure remains same. So once you know u1, sorry, d1 and d2, so we'll going to calculate u1 and u2. Okay, and already we know alpha 1. Okay, so easily we can calculate what is vu1. Okay, so write the inlet and outlet velocity triangle. Okay, check the condition. If u1, sorry, vu1 is greater than u1, then no need to modify the velocity triangle. Okay, but here once again we have to modify it. Next, calculate what is beta 1 and beta 2. Okay, so I'll going to wind up unit 2 here only. Okay, so once again I'll going to glance what is in the unit 2. So unit 2 is completely hydraulic turbines. So I'll go to show here. So I'll take 1 or 2 minutes. See, hydraulic turbines. One is in a classification, general layout of hydraulic turbines, different heads and efficiencies. So already we covered Pelton wheel. In the Pelton wheel, velocity triangles and work done equation. And work done equation, in that only, okay, already we derived. So that is the maximum hydraulic efficiency. Okay, maximum hydraulic efficiency. So with a neat sketch, okay, explain the working principles of Pelton wheel and problems. Next, Francis turbine. So velocity triangle, runner shapes at different blade speeds, efficiencies and problems. Okay, so this is the complete unit 2. Okay, if you will get any doubt, okay, so please note down your doubt and you can ask in the next class. Okay, so we're going to see at 11 o'clock. Okay, so I'm going to start unit number 3. Okay, I will send Shubham Birje. I will send the notes. I'll going to post in the classroom. Okay.
Thank you, sir.
I'm audible? Okay. So next we'll move to unit 3. So that is only the off unit, centrifugal pumps. So here we can see, first I'll go for the your syllabus. So classifications of centrifugal pumps and the principal parts of centrifugal pumps. And here you can see the different heads and efficiencies of centrifugal pump. And here you can see the minimum speed for starting the flow. Okay, so whatever this minimum speed for starting the flow, it is an a the derivation, it is an a simple derivation. Okay, it is an a off page derivation. And the maximum suction lift, one is an a cavitation, need for priming, pumps in series and parallel. See, whatever in your syllabus, okay, so it is a single stage centrifugal pump in your syllabus. Okay, we don't have the multi stage centrifugal pump. I think in the lab, okay, already you studied the multi stage centrifugal pump. But in the theory, okay, we're going to see only a single stage centrifugal pump. Okay, after here we can see the pumps in series and parallel, and the simple problems on centrifugal pumps. So in unit number 2, okay, in the starting classes, okay, we discussed regarding one is a power generating turbo machine and a power absorbing turbo machines. See, turbo machine is nothing but if you take any turbines, okay, if you take any centrifugal pumps, if you take any blowers, all this we can call it as a turbo machines. Okay, but while coming to this centrifugal pump, okay, so I'll going to call it as a power absorbing turbo machines. Okay, power generating turbo machines is nothing but, okay, whatever the kinetic energy, okay, is converting into mechanical energy. Further, that mechanical energy is converting into electrical energy, so that we can call it as a power generating turbo machines. Examples, any turbines. But while coming to the power absorbing turbo machines, okay, so it is in a reverse. Okay, it is in a reverse. So initially we have the electrical energy. By supplying that electrical energy to the mechanical energy, okay, so that mechanical energy is converting into pressure energy. Okay, so that we can call it as a power absorbing turbo machines. Example, centrifugal pumps, blowers, etc. Okay. So while coming to this the centrifugal pumps, see here the hydraulic machines which converts the mechanical energy into the hydraulic energy are called pumps. So just now I told, okay, so once we supply the electricity to the pumps. Okay, here instead of calling a pumps, okay, so I will call it as an a, okay, mechanical energy. Further, that mechanical energy is converting into hydraulic energy or the pressure energy. So that we can call it as an a, the centrifugal pumps, or simply we can call it as an a pumps. Okay, for this, okay, for this, I'll going to call our house pump. Okay, I'm audible. I'm audible.
Yes, sir. Yes, sir.
Yeah. Okay. So I have one question. Okay. So we have the sum. Okay. From this sum, we have to supply water to overflow tank. So how we will going to supply the water? How you will going to supply the water? By using
Using
some
the pump,
method?
sir.
Yeah, using the pumps. But initially or in general, you will going to call it as an a pump.
Motor, sir.
Simply we can call it as a motor. See, once we will going to put switch on, once we will going to on that switch. Okay, so simply we can call it as a motor. Go and put a switch on the motor. Okay, yeah, there is a motor. So that we can call it as an electrical energy. Okay, that electrical energy is converting into mechanical energy. Here, mechanical energy, I will call it as an impeller. So later I will show in the diagram. Okay, later I'll going to show in the diagram. So that electrical energy, okay, is supplying to the mechanical energy. So that is an impeller or a blades, okay, or the turbine blades. So not turbine. Initially, we simply we can call it an impeller blades. So that blades, okay, is converting into pressure energy or the hydraulic energy. So that we can call it as an a pumps. Okay, later I have one small video. Okay, so I'll going to show that video. I hope you understood the power absorbing turbo machine. Okay, so the hydraulic machines which converts the mechanical energy into the hydraulic energy is called pumps. So hydraulic energy is in the form of pressure energy. Okay, so that is the centrifugal force acting on the fluid. Okay, the impeller will start rotates. Once the impeller rotates, okay, so there the force is acting, so that we can call it the suction force is acting on the fluid. Okay, on the fluid. Then the centrifugal pumps acts as a reverse of an inward flow reaction turbine. See, yesterday I told, okay, yesterday I told uh, while drawing the velocity triangle for Francis turbine. Okay, so inlet velocity triangle and outlet velocity triangle, but here everything it is completely reversed. See, the centrifugal pump acts as a reversed of an inward radial flow reaction turbine. So completely it is a reversed. Okay, so for inward flow radial turbines. So I think now you got my point here. Okay, so once we'll go for the velocity triangle and efficiencies, then clearly you can understand so why it is reversed. So next, the centrifugal pumps works on the principle of forced vortex flow. See here, what is that forced vortex flow is nothing but the casing. So there is a different types of a casing. Okay, so based on that forced vortex flow, this centrifugal pumps is based. Okay, centrifugal pump is based. So here clearly explained. So mass of liquid is rotated by an external torque. Okay, means we are supplying. Okay, we are supplying the electricity. Okay, we are supplying the electricity. Then the rise in pressure head of the rotating liquid takes place. Okay, so once we are supplying the external source to that impeller, so in that impeller, the pressure head, or we simply we can call it the suction head, will create. So inside that casing or through that impeller, then the water will start to lift. Okay, the starter will start, so the water will start to lift. Okay, so here we can see, this is only for your simple understanding. Okay, so here we can see the suction. Okay, so here we can see the suction pipe, and here we can see the discharge or delivery pipe. Okay, in between these two, so here we can see the impellers. Okay, here we can see the impeller. So whatever this, we can call it as an impeller blades. Okay, and this outer portion, okay, we can call it as an casing. This outer portion we can call it as an casing. So up this side, okay, whatever the, we can see the suction head or this side. Okay, so there is an a motor. Okay, there is an electric motor. Once the motor will start rotates, means we have to give the external energy to that. Okay, then the impeller will start rotates. Okay, impeller will start rotate. Once the impeller will start rotates, okay, so there the pressure will create inside this. Once the pressure will create, then the water will start to lift. Okay, so this is the basic principle of centrifugal pump. So next, here we can see the centrifugal pump works on the principle of a forced vortex flow, which means that when a certain mass of liquid is rotated by an external torque, the rise in pressure head of the rotating liquid takes place. The rise in pressure head at any point of the rotating liquid is proportionally to the square of the tangential velocity of the liquid. So here we can see the rise in the pressure head, because the centrifugal pump is nothing itself. Okay, it is a pressure. Okay, it is a pressure. Head of the rotating liquid is proportionally to the square root of tangential velocity of the fluid. Okay, of the fluid. So that is, we can simply, we can call it as rise in pressure head is given by omega square into r square by 2g, or simply we can call it as an a v square by 2g. See, please remember these equation, because while deriving the derivation, okay, so we'll go into consider this rise in the pressure head. Okay, rise in the pressure head. So that's why please remember this omega square into r square by 2g. So then only, okay, the water will start lift. Okay, then only the water will start lift. Thus, at the outlet of the impeller, where radius is more. See, please note down this point. Okay, please note down this point. But in the Francis turbine, it is completely reverse. Okay, in the Francis turbine, it is completely reverse. Thus, at the outlet of the impeller, where radius is more, then the rise in pressure head will be more. Okay, but in Francis turbine, okay, what about the pressure? Pressure will gradually decreases. Okay, the pressure in the Francis turbine, it is gradually decreases. But in the centrifugal pump, okay, we can check, okay, at the outlet, the radius is more, then the rise in the pressure head will also be more. So next, then the liquid discharge at the outlet with a high pressure head. Okay, so if the radius is more, then the rise in the pressure would also be more. So then the liquid discharge at outlet with a high pressure head. So please note down this point. So because by using this, okay, we will going to draw the velocity triangles. Okay. So due to this, the liquid can be lifted at a high level. Okay, at a high level. So later we can check. So whether we want pumps in series or a pumps in parallel. Okay. So but if we take, okay, a 10-store building, okay, so we can lift the water to 10-store building also. Okay, if you take, okay, it is in a 50-store building, even for 50-store building, okay, so we can lift the water. Okay, so means it required the high pressure head. Okay, so I hope you understood the introduction. So if you have any doubt, you can ask your question. So no doubt.
Sir, how many more classes will it require to complete the syllabus?
If you'll give another 3 classes, I will complete.
Okay, sir.
So by next week, I will going to complete the fluid turbo machines.
Okay, sir.
This is your doubt.
No, sir, I just wanted to know.
Yeah. Okay. Okay. Next, will come for classifications of centrifugal pump. Okay. First, while coming to the according to the number of impellers. Okay. So before going to this, before going to this, okay, so here we can see how the centrifugal pump will work. So this is the sump and this is the overflow tank. Okay. So and this we can call it as an impeller, and this is completely it is an a casing. Okay, this completely we can call it as an a casing.
So why we have to add that vacuum gauge?
Where see here, because in the sump, okay, so we should know the vacuum level. So that's why, okay, they showed the vacuum gauges here. So other side it is connected to the electric motor, but here the motor is not shown. See how once the water is entered here, okay, so immediately it will start to rotate. So the impeller will start to rotate, and we can see what is the diameter here or the gap here, and what is the gap at the outlet, because this is very important. Okay, this is very important. So here whatever the gap or the diameter, it will gradually increasing. See, so that's why we can call it as it is a volute casing. So next, while coming to the classification of this centrifugal pumps, one is according to the number of impellers. Okay, according to the number of impellers. See, impellers is nothing but it is an a turbine blades. Okay, it is an a turbine blades. So here we can see in this diagram we can see this is one impeller. Okay, so here we can see 1, 2, 3, and 4 impeller blades. Okay, so this complete we can call it as a single impeller. Okay, so like that. Okay, if we have another one, okay, similarly if we have another one, so that we can call it as a two impellers or three impellers or n number of impellers. So that is, okay, that is based on the number of impellers. So whether it is a single stage pump or it is a the multi stage pump. In a single stage pump we have only one impeller. Okay, so in the multi stage, okay, it is a more than two, so that we can call it as a multi stage pumps. So next, according to the position of shaft, according to the position of shaft, so obviously one it is a vertical shaft, so another one is a horizontal shaft. So next, according to a head, okay, so one is a low head pumps, so another one is a medium head pumps. So everything it is based on the applications. Okay, so everything it will come under. Okay, so based on the applications, okay, so we can use this single stage, multi stage, vertical or horizontal, or it is a low head pump, or it is a the medium head pumps. Okay, so these are the uh, classifications of the centrifugal pumps. So next, if we'll go to the main parts of a centrifugal pumps. Okay, if we'll go to the uh, main parts of the centrifugal pumps are the components of the centrifugal pumps. Okay, so first, so here we can see this is the sump level. Okay, this is the sump level, and whatever the delivery pipe. So here we can see the overflow tank. Okay, or the delivery, so where we want. Okay, so this is the sump level and this is the overflow tank. In between these two, okay, we can see the centrifugal pump. Okay, so first this we can call it as the suction pipe. Okay, so below the sump level, okay, we can see the foot valve with strainer. Okay, why this foot valve is required? Because see, once the water, okay, once the water will start lifting, so immediately whatever this foot valve, okay, whatever that full, it will start open. Okay, then the water will start lifting. Okay, then the water will start lifting. Once the motor is completely off, then immediately this foot valve, okay, it will go into close. Okay, it will go into close. So the reason, okay, I will going to tell in the later stage. So we have the cavitation, everything. Okay, so there we'll going to see why the foot valve is required. Okay, with a strainer is nothing but to the filtration, because if there is some impurities in that water, okay, so the strainer is required. So next we can see the suction pipe. Okay, this suction pipe, one end is connected to the, see, one end is connected to the pump. So this is the centrifugal pump. So one end is connected to the centrifugal pump and another end dips into the water in a sump. So this is the one end. So one end it is dipped in the water and another end it is connected to the centrifugal pump. So this we can call it as the suction pipe. Okay, see, suction pipe, one end it is connected to the centrifugal pump. Okay, another end it is in a water or it is in a sump. Okay, so next I'll come for delivery pipe. See, this delivery pipe whose one end is connected at outlet of the pump. See, this is the inlet. Okay, this is the suction pipe, one end is connected here. Okay, and whatever this delivery pipe, one end is connected to the outlet of the pump. So this is the outlet of the pump. So here we can see the outlet of the pump and other end delivers the water at a required height. Okay, so I'm stating here it is a required height. So this is the another end. Okay, so deliveries the water at a required height is known as a delivery pipe. So one is a suction pipe, another one is a delivery pipe. So next I'll come for the impeller. So this is the impeller. So this is the shaft. On the shaft, okay, we can see the impeller. The rotating part of a centrifugal pump. See, this is the rotating part of a centrifugal pump is called impeller. It consists, so here you can check, it consists the series of backward curved vanes. Okay, so whatever the impeller, okay, so it will going to rotate in a anti-clockwise. Okay, it will going to rotate in a anti-clockwise. So instead of calling that anti-clockwise, we can call it as a backward curved vanes. Okay, this is the backward curved vanes. The impeller is mounted on the shaft. So just now I told the impeller is mounted on a shaft which is connected, okay, which is connected to the shaft of an electric motor. So another side, okay, another side we can see the electric motor. Okay, so this is an impellers. Okay, this is an impellers. So impeller, it is a rotating part of a centrifugal pump. So it consists of a series of a backward curved vanes. Okay, so this impeller is mounted on the shaft which is connected to the shaft of an electric motor. So next casing. Okay, next is a casing. The casing of a centrifugal pump is similar to a casing of a reaction turbine. Okay, so I will going to show the casing of a reaction turbine. You just check it once. Yeah, you just, this is the reaction turbine casing, and I will going to show the centrifugal pump casing also. Okay, so both are similar. Okay, both are similar. Got it? See, the casing of a centrifugal pump is similar to the casing of reaction turbine. See, it is whatever the centrifugal casing. Okay, it is an airtight passage surrounding the impeller. Okay, so here we can see it is an airtight passage surrounding the impeller, and it designed in such a way that here we can see, okay, it is an air tight passage surrounding the impeller and is designed in a such a way that the kinetic energy of the water discharge at the outlet, and the impeller is converted into the pressure energy before leaves the casing and enters the delivery pipe. Okay, see here the gap between, so at the inlet, here at the inlet, the gap between the impeller blades and the casing is very less. It means, okay, so whatever the whirl, okay, it is a very less, or it is in a very minimum at inlet. Okay, so I'll repeat once again here. The gap between the impeller as well as the casing, okay, is very less. Okay, so there, whatever the whirl, so it is in a very minimum whirl is there. But while coming to the outlet, okay, while coming to the outlet, the whirl is maximum. Okay, the whirl is maximum. Okay, so based on this, okay, we will going to draw the velocity triangles. While writing the velocity triangles, once again I will going to highlight here. Okay, while drawing the inlet and outlet velocity triangles, okay, so once again I will going to highlight here. Okay, so this is the casing. So there is a different types of casings are there. Okay, there is a different types of casing. So take here, I'm not shown. So one is a volute casing. So here you can check. One is a volute casing. Another one is a vortex casing. Okay, and casing with guide blades. Okay, so another one is a casing with guide blades. So there is a three different casings. So one again, it is depending on the applications. One is a volute casing, one is a vortex casing. Okay, another one is a casing with guide blades. Okay, so and here you can see the impellers. So this is the one impeller, and this is the foot valve with stainer, and this is the foot valve with stainer. Okay, so the main parts of the centrifugal pumps is foot valve with stainer, suction pipe, delivery pipe, okay, impeller, and another one is a casing. So instead here in the centrifugal pump, we are not calling it as a blades. Okay, instead of calling a blades, okay, we're going to call it as a impellers. Okay, and I'll going to continue tomorrow. So we're going to see the different heads. Okay, same in the same diagram only. So here we can check the different heads, because while solving the problems, okay, so these heads are very important. Okay, so you have any doubt, you can ask. If you have any doubt, you can ask. Okay, no? Okay, so I'll going to wind up here only. We're going to see in the next week. Thank you.
Thank you, sir.
Thank you, sir.